Why is the far side of the moon unique for astronomy? How can astronomers use radio telescopes on the far side of the moon to explore some of the earliest epochs in the universe, a time before galaxies and before even the first stars? In this episode of Chai on the Moon, we have a conversation with Professor Jack Burns, who has been thinking about these issues for the last 40 years. Hello, and welcome to Chai on the Moon. This is a series where we talk about societal and ethical issues related to future human settlements on the moon. In this episode, we have our special guest, Professor Jack Burns. He's a Professor Emeritus in the Department of Astrophysical and Planetary Sciences and Professor Emeritus in the Department of Physics, both at the University of Colorado Boulder. He's Vice President Emeritus for Academic Affairs and Research at the CU Systems. And there are other things as well. But for me, the most important thing is, and I think for other people too, is that I have known Professor Burns from his days as the chair of the astronomy department at New Mexico State University in Las Cruces, where I got my PhD. Professor Burns was at that time the chair, so I've known him for a while. And so, welcome, Professor Burns.
Thank you, Salman. It's so great to see you again.
Thank you. And I should mention that just in case, I'm carrying Pluto,
Oh,
never
yes.
forget mug. So I'm having coffee because the department in New Mexico and NMSU Las Cruces was founded by Clyde Tombaugh, the discoverer of Pluto. And so for us, it will always be a planet.
And Salman, of course, you remember that Professor Tombaugh was still on the faculty in his
That's right.
90s and still coming in every day. And he would get pretty angry when people would suggest that Pluto was not a planet. So
I know.
he was a feisty guy.
I'm pretty sure it's an apocryphal thing, but story. But the way it was framed was because I was still in grad school when he passed away, and it was like that. His last words were, "Don't take Pluto away from kids."
Something to that effect. But one of the things that is so um, rewarding is that Alan Stern was able to get a small bit of Clyde's ashes and include them on the New Horizons spacecraft that flew by Pluto. Because we all remember Clyde saying numerous times, "I want to be the first man on Pluto." So, effectively he was, at least with this ashes that made it there. So that all brought a little tear to all of our eyes.
That's right. So, well, let's. But the other thing I remember again. So we are still talking about the historical sense. One thing I remember, and in the department was that outside your office over there, there was a artistic rendering. There was a, I guess, a painting of a telescope on the moon, and I think that was one of your sort of like dreams in some sense. So now there are a lot of people talking about, and we are going to spend a lot of time chatting about that. But I'm talking about 30 years ago, and you were already thinking about that at that time.
Well, Salman, if you can look behind me, there is on the wall is a couple of pages of a Scientific American that we published in 1991 that had that artist's conception of radio telescopes and other telescopes on the moon. So it has been a long time coming. The first presentation that I was invited to give about a radio telescope on the moon was in 1984. So it's now 40 years of advocacy. And finally, this year, we had our first radio telescope on the moon.
All right, so we'll come back to it. And I should say, if people think, oh, that's a long time, but like the idea of a space telescope, for example, had been around for decades before Hubble Space Telescope went up. And so these things do take time and it takes a longer vision. So let's directly dive into it. Why care about having a telescope on the moon?
Yeah, it's a great question, and a question I asked myself when I was first approached by a fellow lunatic, that is a lunar geologist named Wendell Mendel from Johnson Space Center in 1984. We were serving together on a high school science fair judging team in Albuquerque, and he was organizing a session, a special workshop at Johnson later that year on a return to the moon. It had been more than a decade since the end of Apollo, and there was a renewed interest. And so he asked me about it, and I had about the same reaction. Why would I want to put a radio telescope on the moon? Well, starting to think about it and recognizing that, in particular, the far side of the moon is a truly special place in the inner solar system because it's really the only radio quiet zone that we have. On the surface of the Earth and even in orbit of the Earth, there are radio transmissions, human made radio transmissions, that cover the entire radio spectrum, and it blanks out your ability to be able to observe details, sensitive observations. And then, in addition, the ionosphere of the Earth, it actually distorts beginning at around 100 megahertz and below, and then actually absorbs radio emission mostly below 20 megahertz. So we can't even see that part of the spectrum. So the far side of the moon, being this 2,000 kilometer chunk of rock, blocks out radio emissions coming from the Earth, and the moon itself has very little ionosphere. And so making observations all the way down to tens of kilohertz, well below the ionosphere cutoff on the Earth, becomes possible. So the moon, the far side of the moon in particular, allows us to open an unexplored part of the electromagnetic spectrum. And as it turns out, one of the science cases, namely the dark ages and cosmic dawn, is also one of the last unexplored epochs in the early universe.
Can you say a little bit more in the sense that, I mean, for people who are not familiar with the Dark Ages, because some people worry that with the next elections, we may be heading into some sort of Dark Ages, but for the universe, if you want some cosmic perspective, what are the Dark Ages, and how can telescopes on the moon explore that?
Yes, yeah, and so the Dark Ages and Cosmic Dawn. The Dark Ages start off right at the time that the cosmic microwave background becomes visible. And what is that? That's called the epoch of recombination. This is the first time in the universe in which electrons and protons combine together and produce hydrogen atoms. And in the process, they allow the universe to be transparent, and we can see those first flickers of light from the very early universe. So that begins our observational time period. And we've had a number of NASA and ESA probes, as well as ground-based telescopes, look at what's called the CMB. And several Nobel Prizes have been awarded for that. Starting at that time period, though, the universe is filled with neutral hydrogen. Um, but there are no stars, no galaxies yet. So using telescopes like Hubble or James Webb, you can't see anything because there are no sources of optical or infrared light, and no stars or galaxies. But again, the universe is full of neutral hydrogen. And so we can use the famous 21 centimeter line of neutral hydrogen that emits in the rest frequency. But by the time it reaches us, with the expansion of the universe, it has been stretched to much longer wavelengths, hundreds of meters, tens of meters, I should say, to 100 meters, and frequencies below the FM band. So you need to use low frequency radio telescopes to be able to see that epoch of the Dark Ages, which, although there are no stars and galaxies, there's a lot going on during that time. You have the collapse of the first halos of stars and galaxies. And we can see that through the hydrogen interactions and the variations in the hydrogen, both the spectrum and the angular fluctuations that occur. And so, roughly 100 or 200 million years after the Big Bang, then those collapsing halos form the first stars and galaxies, and that's the cosmic dawn. And that
So,
too we can probe with our radio telescopes.
so if we connect, and a lot of people are familiar with the earliest galaxies that James Webb Space Telescope is finding. So those are around 250 or 300 million years. And people are surprised that, well, they seem to be, some of them at least, have well formed disks, or somewhat have disky shape, or at least one of them does. What you are talking about is that they're probing the time before that, of what led to the formation of those very first galaxies, which James Webb cannot look at it, but a telescope on the moon can.
You're exactly right. And in fact, the recent observations of the James Webb Space Telescope have made these radio observations even more important because something more is going on in the early universe than we had anticipated. Stars are forming a little bit earlier, active galactic nuclei, giant black holes are forming earlier than we thought. So, what's going on? But at this stage, we're pushing already the James Webb Space Telescope about as far as we can, because beyond that, things are just simply too faint. But with the radio telescope, we can probe all the way through that and even into this dark ages before those stars form. So that missing physics that may be going on, and that may have something to do with the nature of dark matter. It could also have to do with the formation of neutrinos in the early universe, even an early epoch of dark energy that involve all this interesting exotic physics. The Dark Ages is a playground for us to really investigate new physics and some of the missing physics that may be part of our that are not currently part of our standard models of physics and cosmology.
And so if we can go in terms of talking about the moon, what kind of a telescope? I mean, you've mentioned radio telescopes. So for people who don't know, I mean, there are different wavelengths, different forms of light, and radio telescopes. People are maybe familiar with, who have seen Contact, for example. Like, you have Very Large Array, which you also worked with, or they have an image of telescope in Puerto Rico, the Arecibo, which no longer works. Now the largest telescope, single dish, is in China. But I'm just curious. So when we are talking about probing those dark ages and the cosmic dawn on the far side of the moon, what kind of telescopes are we thinking about?
Yeah, so that's an excellent question as well. So these are not the traditional dish antennas. We don't need those. We can use much simpler antennas called dipole antennas, which are just two telescoping antennas. Think of the old antennas that people used to have on their cars, which they would pull up and they would be telescoping and pull up, and that's called a monopole antenna. So just put another one 180 degrees apart, and that forms a dipole antenna. And that is, in fact, the kind of antenna we use for our recent Rolls mission, but also is the kind of antennas that we would lay down in abundance on the far side of the moon, putting down hundreds to thousands to even 100,000 of these dipole antennas, which is part of a NASA-funded study that we're now doing right now called FarView. So very simple antennas, which is great because the moon is still a tough place to get to. The simpler the technology, the more likely it is that we're going to be able to set up these telescopes, and we'll keep the costs down.
Uh, so a couple of roles, as you mentioned, that is the radio wave observations at the lunar surface of the photoelectron sheath. Seems like that's the full full name for that, NASA's acronym. But and you mentioned this stuff that okay, it's easier to put on the moon, and some of the issues that in this series that we have been talking about, and I'm going to push you further later. We're going to talk a little bit about that. Is about, for example, the footprint of humans on the moon, and sustainability. Like, is it sort of like how much environment of the moon we can disrupt and things like that. So when again, for this type of a project, when you are mentioning thousands of these antennas, what would it look like? So for people, I mean, how big are those? What would be the distribution? What are we talking about within craters? Are we talking about outside? And what kind of, how deep they have to be dug in, and those type of aspects?
Yeah, so you got lots of questions there. We'll try to sort through. So for our Rolls's telescope, we had four of these monopole antennas. They were only 2.5 meters long, and
Okay.
they were spring loaded in the mechanism. So we popped them open, and they just shot out when they were on the surface of the moon. So extremely simple, easy to deploy, and we've been for 50, 60 years using those kind of telescopes, radio telescopes in space. So they would look like that. And for an array, what we're talking about, we would just put those, actually lay them on the surface of the moon. So we have done some studies and some modeling of the electromagnetic interaction of these radio antennas with the surface. And because the surface of the moon is so dry, the electrical conductivity is very low. And so, unlike on the Earth, if you do this on the Earth, the antennas would basically short out. But you can put these on the moon, and they would function just fine. So, just laying them down there is what we're going to look at. So, we'd look at cross dipole antennas, so sort of like this. So, we could do the two polarizations, put them down on the Earth, put them down on the moon, and then just one after the other. We're looking at building them in subarrays with probably tens to 100 or so in a subarray, and then another one next to it and another one after that. The concept that we have that these arrays don't need to be very large, relatively speaking, but they still need to have a diameter of about probably 15 or 16 kilometers. Um, and we would put down 100,000 of these antennas into that area, densely packed near the center, and then less so as we move out, kind of like the VLA, which has kind of like a power law distribution of antennas going outward, to give us good UV coverage, that is good coverage of the sky. So they would look like that, pretty simple. Um, not as glamorous to take pictures of like the VLA is, but because these things, in fact, that's one of the things we've been struggling is to get some good
Yeah.
graphics because they don't show up, on a perspective of 16 kilometers, trying to see antennas that are 10 meters tip to tip and just
Yeah.
thin dipoles is challenging.
Well, with a very large array as well. I mean, if you, depending upon the configuration that you go in, I mean, it's great when they are all compact together where you can see all of them, but when they are spread over a couple of kilometers, you don't see all of them. So I'm so a couple of questions regarding that. One is, can that area where, because you're talking about 10, 15 kilometers in
Right.
terms of the coverage, and these antennas are laid on the ground over there, can that location be used for other purposes, or that 15 kilometer diameter area is just for the telescope?
Yeah, I think mainly because we have them packed in so tightly near the core, in particular, the inner 5 kilometers or so really would be hard to imagine anything else. So, unlike at the VLA where people graze cattle we're not going to be grazing any cattle between antennas on the moon. You're not going to be grazing cattle there in any event, but no, you're not going to be doing other things likely. But again, that's a very tiny area on the moon relative to the overall surface area, because you can remember the surface area of the moon is greater than the surface area of North America. So there's a lot of land there.
And following up to that, one of the interesting things right now, the and you mentioned sort of like that some of that has been tested, and that has been tested because I think your some of your experiments were supposed to be the first mission, Astrobotics mission, and then Intuitive Machines as well. And Intuitive Machines was successful. How did that go? What did you find? I mean, because that Intuitive Machines mission did go and land on the moon, even though sideways.
Yeah. So this is all part of NASA's new program called CLIPS, the Commercial Lunar Payload Services Program. And this is something that actually I played a role in helping to create. I was on the US presidential transition team for NASA in 2016 and 2017. And on that team, we proposed what came to be the creation of the Artemis program and the CLIPS program that would complement the human program. And that the then incoming administration and the NASA administrator picked these up, ran with it. And of course, this has continued and even amped up through the Biden administration in recent years. So this CLIPS program has opened up the accessibility to the moon at a reasonable cost. And this is really, people ask me all the time, why is it taking so long to get back to the moon? It's because we had no way to get there, no way to get there with a reasonable cost. But over 50 plus years, the costs have dropped, the technology has improved. And so, as you mentioned, Salman, the Astrobotics was the first of these CLIPS to make an attempt. Of course, they weren't able to land on the moon. We did not have a radio experiment, by the way, on that mission. So the first one we had a radio telescope was on Intuitive Machines. And, we had a beautiful launch on SpaceX. We did have a couple of hiccups along the way, including one of the hiccups was actually our experiment, Rolls's. One of the antennas unexpectedly popped up, and the mechanism that was housing it overheated because the spacecraft wasn't rotating with respect to the sun quite the way we were expecting. So it overheated a bit, popped up. But having done that, when we got the message it was there, we turned on our radio spectrometer and actually took the best data that we have, about an hour and a half along the way. So then we also know that that the lander had some issues trying to land. The laser navigation system was not functioning, so they had to use the optical imaging, which was less precise. So we came in too hot, came in too fast, also had a little bit of horizontal motion, and one of the legs got tripped up, broke, and it caused the lander to topple over on its side. It was elevated by about 30 degrees off of the surface. Nonetheless, we still had a functioning communication system. We had to use our low bandwidth communication because the high gain antenna was pointed in the dirt. So that's never good. But we had the low gain antennas, and we had enough solar power that we were able to deploy the remaining three of our antennas. We were able to take some data. We have about 20, 30 minutes worth of data from the surface of the moon. And so with that, I've declared the dawn of radio astronomy on the moon has occurred. And we have enough data. I talked about this 2 weeks ago at the American Astronomical Society meeting in Madison and presented some of our first results.
All right. So this series we often talk about, and people are familiar with that a little bit, about some of the competing interests, in particular with private companies. And and it's unclear. There are a lot of legal questions as well from international perspective about what outer space treaty allows and doesn't allow, and also what the commercial companies can do on the moon. Now, there is a working group now with International Astronomical Union about the protection of astronomy on the moon. I mean, in some sense, the case that you are making about exploring the dark ages of the universe and the cosmic dawn, in some sense, that can only be done, at least within the practical range, from the far side of the moon. How do you see that play out? And especially because you also are collaborating with some of the private companies, how do you see that interaction right now? And how do you see that sort of like play out in the future a little bit?
Yeah, these are also good questions, Salman, and as you know, I was regularly teaching a class on space policy at the University of Colorado until I retired a year ago. And over the last 10 to 15 years, I've been talking and preaching to our students and preaching to folks in Washington as well that space law and space policy is behind the technological developments that we have on the moon. You could see all of this coming. And the last major international agreement was the Outer Space Treaty of 1967 that basically said no one owns the moon. And there has not been another treaty that all of the major space players have signed since then. So we're behind the times on that and really need to catch up. But I'm a major proponent of private companies and public-private partnerships on the moon because we're taking advantage of the resources that those companies and, frankly, the billionaires who are behind several of these companies are driving this forward, and it doesn't require all public money to be able to do that. So that's great. It, I think, is going to allow us to develop a sustainable infrastructure on the moon a lot faster than we would have been able to do with all government programs. Now, having said that, there's also danger there too, namely the pollution of the moon, in particular the radio quiet far side. So, because a lot of our electronics leak at low radio frequency, so just power supplies, for example, that you have in your computer, it leaks out at just the frequencies we're trying to observe it. And we've seen that recently with some of the SpaceX Starlink satellites that are in Earth orbit. Recently, the LOFAR observatory in low frequency observatory in the Netherlands detected leakage from their power supplies from those satellites, and they're pretty strong, pretty strong. So imagine, thousands of those kinds of satellites in orbit around the moon. That could easily ruin the far side for low frequency observations. So yes, a group of us, Richard Green, whom you've talked to, and I have put together a group with the International Astronomical Union to look at astronomy from the moon. We've got a number of good key players. I've also been working with the International Telecommunications Union recently. They're the ones that set the regulations for protections of frequency bands, both on the Earth, and they actually have already have the permissions to do this for the moon. So we're working now finally on new regulations and making the broader communities, the scientific communities, as well as the technology and industry communities, aware of the harm that could be done if we're not careful around the moon.
And I mean, you are talking about the leakage of electromagnetic signals, basically leakage of light that can come in
Yeah,
and
leakage
interfere.
of radio emission coming
Radio
from
emissions.
yeah from the electronics. Yeah, that's right.
But what about construction on the moon, which may start earlier because of the robotic plans as well? Would that interfere the regolith that gets up because it doesn't have an atmosphere over there, or uh, sort of like drilling or whatever is happening? Are those things going to be interfering with radio observations as well?
Not directly, not with the radio observations, but only indirectly in terms of, once again, they all have power supplies, they all have electronics associated with it. So it's relatively easy to shield, though. I mean, it's just doing what we call a Faraday cage, which is basically chicken wire, literally
Right.
chicken wire. You just wrap your electronics, and that prevents a lot of leakage of this radio emission. So it's not terribly expensive. You just have to be aware of this and prepare to do this. And this is not insurmountable, and it's not telling any company that no, you can't do what you want to do. But you just need to be, a little bit aware. I mean, it's like a company on the Earth. They're digging in Italy, and they uncover a Roman ruin, right? And so they've got to be sensitive to that, and they've got to mitigate that and understand where the harm could be. And similarly on the moon, just have to be aware of mitigation of radio noise and radio pollution.
But I think that is where the tension lies, right? And this also happens. I mean, you mentioned in Rome. I mean, I think those tensions are there. I'm familiar with archaeological controversies, for example, in Istanbul.
Yes,
They were digging around. So okay, so if you find something, and then somebody has to decide on the value, those are ongoing conversations in terms of what is the value of the artifact or the archaeological site versus the benefit to humans. I mean, in some sense, and I would put that in quotes because what a benefit means, especially for private space companies, right? I
yes.
mean, so that gets tricky. So, in that context, you did mention that satellite bandwidths are negotiated with the International Telecommunication Union. How do you think, or what do you suggest can happen on the moon, thinking about these larger issues where you might have these telescopes, not just about the leakage of electronics, but a larger issue, and then you also have commercial interests uh, that that might be coming in, or military interest. I mean, I've not mentioned that, but I mean, there are, even though it is not legal, and again, outer space treaty is a little bit ambiguous regarding that. But how do you suggest, what kind of a framework can protect astronomy?
Yeah. The many on the military side look at the moon as the high ground in space today. And that's not just the US, but it's the Chinese and others. And exactly how that would translate. It's not so much putting missiles in space, but also surveillance activities. So yes, there's interest there. But in terms of communications, the radio communications are at much higher frequencies than
Right.
what we're looking at. So I don't worry about those as much because they're just orders of magnitude away from the frequencies that we're worried about. So I think just a little bit of care is all that would take. And then, as I mentioned before, a little bit of care in packaging your electronics on a satellite, just putting one of these Faraday cages around the electronics would go a long way to take care of it. So the mitigation is a lot easier than it would be in Rome, where you have to stop construction because you see a Roman artifact. In our case, it's no, we don't want you to stop construction. We just want to make sure your construction equipment that you're bringing to the moon has already mitigated the radio emission. So some care. So we don't want to stand in anybody's way because those companies have sharp elbows. They have a lot of money, and so we have to be reasonable in what we ask for. And that's actually what we're doing right now with the ITU and the IAU is to look at at this stage what part of the spectrum we need to preserve, and how we would do that, and do it in such a way that um, that the commercial sector is going to be able to sign on to. Because we've got lots of experience now in these kind of negotiations from the Earth. So we've got decades and decades of doing this. So I think the people who are working this that I've seen have a lot of political experience to be able to do this, and they're able to sit through a lot of these really boring meetings that I have a hard time with, to tell you the truth.
To follow up in that direction, one is that, but there is other science as well. I mean, I know that you're talking about the radio aspect, and I'm trying to push you the sort of like, the broader non particular radio astronomy that you are talking about, but perhaps other wavelengths. There can be other telescopes, but also geological interest that is there. You also learn a
Yes,
lot
yes.
about the solar system, the water in the South Pole, the water ice that is there, that can also tell us a lot about the origins of the solar system and those type of things. So
And at the
in
same
that,
time,
yeah,
Salman, people
yeah,
want to mine that water ice for commercial use to turn into rocket fuel. So
right.
you've got people wanting to dig in these same areas where scientists want to just look at the nature of that ice and try to understand the early formation of the Earth Moon system.
That's right. So for my, so what I would like to know is, like, so in that sense, how do you, since you are working with the commercial interests as well, how do you see us, and us I mean now as astronomers, for example, positioning ourselves in as part of the broader scientific community, which says, okay, well, there are other sciences which may get seriously impacted by commercial, versus particular science which may not get impacted, like, for example, the kind of telescope that you are talking about, by commercial things. How do you see us, and now I'm talking about as astronomers, advocating? What should we be advocating, especially when it comes to sciences that are being impacted but are not related to astronomy
Yeah,
necessarily?
yeah, and so part of it is for us to be reasonable, in understanding that we're unlikely to get everything that we want, and taking that kind of reasonable approach, we find based on Earth-based negotiations, the way we want to do. I mean, we're having huge issues on the Big Island of Hawaii now, in negotiating the 30-meter telescope on Mauna Kea, with the native Hawaiian population. And that is extremely challenging negotiations. And so we have developed some experience now that I think we can apply, and some lessons learned that we can apply to the moon as well. So whether or not we want to preserve a permanently shadowed crater to not only mine water ice, but maybe to put a millimeter, submillimeter telescope in there, so that we can use the fact that that crater is at an equilibrium temperature of 30, 40 Kelvin, and is all cooled and can do some phenomenal observations of the early universe, and someone wanting to get their mining tools down there and extract that water ice out of there. So the good news is there's lots of potential craters that are permanently shadowed and have water ice. So one has to undertake negotiations. So I would just say at this stage, we're starting the process now, which is good. And we should have started it 10, 20 years ago, but no one thought then very seriously that we would be working on the moon like we are now at that point in time. So now we have to do some catch up. But I think there are lots of lessons learned, and if everybody's reasonable in approaching this, and there are some international governmental regulations, then we can figure this out.
Yeah, and you mentioned Mauna Kea, or Hawaii, the telescopes in Hawaii, which is a great example, because there was a precedence to that in Arizona, in fact.
Yes.
There was Mount Graham Observatory, much more controversial, and of course then controversy continued, and the issues of Native Hawaiians are a bit different than of Native Americans for various historical and political reasons. But to a certain degree, and you mentioned the ashes of Clyde Tombaugh on a New Horizon mission to Pluto, but Astrobotics mission was taking human remains of Shoemaker. Actually, no, Shoemaker one was in the 1990s, but a lot of Star Trek
Some of the Star Trek folks, I think Scotty
folks
and several others, yeah,
and
they were,
Uhura and
yeah,
others were on it,
and
and
others were bringing that, and that was being very insensitive to the Native Americans who view the moon as a sacred ground. And so, how do you negotiate that? So
right.
that's people really weren't thinking about that. So we're going to run into a number of things like this. I mean, similarly, how about the original Apollo sites, Apollo 11? Now that we have the capability of private companies to be able to, on their own dime, go to the moon, what's going to stop some of these companies from, uh, uh, a rogue company landing and digging up some of the first footprints from Apollo 11, bringing them back and selling it on eBay? I mean, that's horrific to think about that somebody would do that, but what's to stop them at the moment?
Right, and so that is where I want to focus towards the end, and that is how do you see those kind of regulations coming in? You mentioned that we have to be reasonable about it, but of course, as we have seen with Mauna Kea uh, discussions as well. I mean, because oftentimes people are talking about two completely, in some sense, orthogonal values, right? I mean, so for one person, something is of value, whereas the other person, something else is of value, and they are orthogonal, and that's where the conversation goes. So, how do you see, since you are deeply involved, and the reason I'm pushing you is because you have an interest and you are actually really working on it. And I think there is an argument to be made that astronomy is really unique and it cannot be done anywhere else, the kind of astronomy that can be done on the far side of the moon, right? Nevertheless, these issues that are not just from the space companies, so space companies can decide what the values are, but they don't speak for everybody. So how do you see, again, I come back to, as astronomers, how do we see that? And you taught a public policy class. I also developed a public policy class a while back, and in some sense we have to frame our conversations, right? I mean, like, that even for astronomy we have to frame how do we see what we are doing and how do we see it in the larger global human sense. So this is where I'm trying to get, how do you see a framework potentially that can start the conversation in a proper way?
Yeah. So, Salman, here's where astronomers have a real advantage. What we do is perceived by the public and by folks on Capitol Hill as being really cool and really important. I've had, as you probably have, I've had many conversations with members of Congress, congressional staffers, and served on various committees and so forth, right up and into the White House. That when you talk about astronomy, you talk about some of the things we just talked about, the early universe, the cosmic dawn, and the dark ages, and being able to observe exoplanets also with these telescopes. People look at that and say, "Oh man, this is cool. We got to do this." Okay, and so you capture their attention right there and their passion for this right away. So when it comes to governmental regulations in particular, we have those advantages that people recognize the importance of astronomy and, of course, are willing to spend tens of billions of dollars, like the James Webb Space Telescope, on astronomy. I mean, we're a small community. I mean, the American Astronomical Society has 7,000 members at the present time. And look at the tens of billions of dollars of telescopes. No other science field has anything close to this kind of governmental investment in infrastructure that astronomy does. So I would start off with that, with the cool factor, telling people, as we're doing today, that we can do these unique things from the moon with our telescopes. And so let's start off there and figuring out how we can protect our sites in order to make this kind of information, these kinds of data available to the general public.
All right. Towards the end, what do you think? In 10 years, or when do you see, like, if I were to ask you around 2050, right?
Well, good luck with that. If I'm still around in 2050, I'll be approaching 100 years old at that point. So that's pretty good.
You may still be able to run for president, right? But so by 2050, more realistically, how do you see what will be happening on the moon?
Yeah, I see the moon as a thriving place that will have a lot of commercial interests. I can see having private hotels, regular visitation there. Whether or not you have a Disneyland on the moon or something like that is hard to say. But there'll be that kind of commercial interest. There will be manufacturing on the moon. They'll be extracting minerals as well as water ice and probably making rocket fuel, which will be a lot cheaper to do on the moon. And the moon basically as a base that we can use to then explore the rest of the solar system. In many ways, the moon is probably a better place to start in terms of travels to Mars than actually starting from the surface of the Earth. So the moon will be our stepping stone to the rest of the solar system. By 2050, I would hope we would getting close to getting to Mars, although it may take a little bit longer. So, but I think the moon will continue and will remain as our first serious steps towards being a true interplanetary civilization.
And is there any, from astronomy perspective, uh, what do you think can be surprising from the perspective of the dark ages or the cosmic dawn? Do you expect something that can really, would be out there, surprising result that can potentially come out?
Yeah, I think they could. I mean, we know, for example, that our standard models of physics and cosmology are not the end all. There are things missing. And whether it's linking gravity to the other three fundamental forces in the universe, we haven't figured out how to do. Something is very different about gravity from the other forces. And so exploring new epochs in the universe, like the Dark Ages, which are particularly simple because the Dark Ages have no astrophysics at that point. So it's all just, no stars, no galaxies. There's just physics. And so looking at this particularly early time, if there are signatures of additional missing physics, this is where they could pop up. And the radio is the place to be able to start looking for those. So, the far side of the moon, the dark ages, could be a gateway to really understanding a lot more about our broader universe, about physics and cosmology than we do today. That's a potential that's there, Salman, at least. And so that's what keeps me going.
That's great. And I would have finished over there because that would have been a great ending. But of course, I have to spoil it. And, and I have to ask you one other question. And that is, other than the moon, do you think there are other bodies where this kind of science can potentially be done? Or the far side is really unique in our ability? I mean, access is certainly because it's closer to us. But in the solar system, I mean, do you think there are other places where we put and say, like, well, this is actually better than the far side or something like that?
Yeah, I mean, the far side is mainly shielding ourselves from Earth emissions as well as shielding from the sun at night. So just going further out from the solar system. But as you said, accessibility is the problem. I mean, the nice thing is the moon's only 3 to 5 days away. It's easy to get to, has these unique capabilities. But at other wavelengths, space observatories like James Webb, gamma ray observatories are going to continue to be built in space, and probably the Earth Sun L2 points. Those are great places for location. But maybe, on the moon, we'll end up with low frequency telescopes. Maybe we'll end up with new gravitational wave observatories, arrays on the moon, cosmic ray observatories on the moon. So I see this as a combination. The moon is just one of a number of landscapes for us to put our telescopes on.
Well, Professor Burns, that was amazing. That was really wonderful to talk to you, and good to reconnect with you after many years. So thank you so much.
Indeed, Salman, it was a great joy to be with you today.
Thank you.